All right, ladies and gentlemen, we're looking at section 8.4 today, dealing with polar coordinates, graphs. In other words, we want to talk about the basics of how graphs of polar equations are created. And when I talk about the basics here, I mean the very basics. We're not going to get into much detail at all. Okay? Now, the one thing I'm going to discuss in this video is the idea of symmetry. Which is a tool to help us graph more easily and accurately. Okay? So it makes it easier, but it also makes the graph more accurate for us when we understand the graph. Okay? Now, there's three types of symmetry. That our graph may have. Okay? The first type, symmetry about theta equals pi over 2. Now, theta equals pi over 2, if you're thinking about your polar axis is here, at theta equals 0, theta equals pi over 2 is here. That means it's symmetry about what we normally would consider the y-axis, a vertical axis symmetry. That's what we're talking about here. Okay? The second type of symmetry is symmetry about theta equals 0, which is the polar axis itself. So that's symmetry about the horizontal axis, what we would normally think of as the x-axis. But here it's not called the x-axis, it's called the polar axis. So this is symmetry about the polar axis. And the third type of symmetry is symmetry about the pole itself. What is the pole? Well, on your polar graph paper, this is the pole right here. So symmetry about the pole is another way of saying origin symmetry, as we would refer to it on the xy plane. Okay? All right, now there's a test we can run for each type of symmetry. For the first one, the test is that we take our equation and we replace the r and the theta with a negative version of each. If the equation remains the same, then we know we have this symmetry about theta equals pi over 2. The second test, it's also a replacement test, but this time we only replace the theta with negative theta. If the equation remains the same. Then we have symmetry about the polar axis. And the third test, think about this. The first test, you replace both with their negative versions. Second test, you replace the theta with negative theta. So not surprisingly, the third test is you replace r with negative r. And if the equation remains the same, then we have symmetry about the pole. Okay. Now, the interesting thing about all these tests is they say the following. If you do the replacement and the equation is the same, then you know about a certain type of symmetry. Okay? Passing the test implies a type of symmetry. Okay? But what is not true is that failing the test implies no symmetry. Failing the test does not imply no symmetry. In other words, you could fail any one of these tests and still have the symmetry that's being discussed. So this is not a perfect test. If you pass the test, you have a conclusion. If you fail the test is inconclusive. Passing the test is conclusive. Failing the test is inconclusive. It does not tell you that you do not have a certain type of symmetry if you fail the test. It's only that if you pass the test, then you do know you have a certain type of symmetry. And we're not used to seeing many things that work that way in math, so you kind of already may have been assuming that if you failed the test, that meant you didn't have that type of symmetry. So you have to be careful not to think that way. Okay? All right, so let's take a look at a couple of examples now. Okay, I'm going to take a look, toggling down through the section to the exercises. I'll get there eventually. Okay. In exercises 6 through 15, the prompt says, test the equation for symmetry. And so let's take a look at problem number 6, where we're given the equation r equals 5 cos 3 theta. And let's run our 3 tests on this. Okay, test 1. Test 1 again is we're going to replace the r and the theta with a negative r and a negative theta. And the question is that the same equation as up here? Well, let's work on this. 3 times negative theta is negative 3 theta. And now what do you know about the cosine? You know the cosine is a function that consumes the negative on its argument. So that negative goes away. And what you see here is not the same as the original equation, meaning that the test failed. Test is inconclusive. I don't know if I have this type of test 1 symmetry, the symmetry about theta equals pi over 2 or not, based on this test result failing. Okay. Test 2. In test 2, where we're testing about symmetry about the polar axis, we're replacing theta with negative theta. So the only replacement that's done is right here. Just like up here, that's a negative of 3 theta, and the cosine consumes its negative. And that is exactly the same as the equation we started with up here. Okay, we pass the test. We for sure have symmetry about the polar axis. And in test 3, if we run that one, that's where you replace the r with negative r. There's absolutely no simplification that can be done. This is not the same as the original equation. They differ on the r, so we fail the test. It's inconclusive. meaning I don't know if I have origin symmetry or not. Just like up here, I didn't know if I had symmetry about the line that equals pi over 2 or not. But what I do know for sure is I have symmetry about the polar axis for this equation in number 6. Okay? All right, let's take a look at problem number 8, where r is given as 3 plus 2 sine theta. Test 1. You're going to replace both the r and the theta. Now, sine function spits out its negative. So that's what we get. That is not the same as this up here. And if I multiply it through by a minus, we get a minus 3 plus 2 sine theta, which is not the same as what's up here. So the test fails. And it's inconclusive as to whether we have that symmetry about the line theta equals pi over 2. Test 2. You replace the theta with negative theta. Well, the sign again spits it out, the negative. That's not the same as the original equation. Test fails. This is inconclusive. Maybe I have symmetry about the line polar axis, and maybe I don't. This test doesn't tell me. Test 3. You replace the r with negative r. That is not the same as the original, so test fails. It's inconclusive. I don't know whether this equation has symmetry about the origin or the pole, as we say, or not. The test doesn't tell me whether it does or doesn't. Okay. All right, problem number 10. Very simple. R equals 4. Test 1. You're going to replace the r and the theta with a negative r and the negative theta. So we get that. Okay. Is that the same equation? No. So it's inconclusive. I don't know whether we have symmetry about this pole or not. Okay. The test failed, so I don't know. Test 2. You replace the theta with negative theta. Well, there is no theta, so when you replace the theta with negative theta, you still get r is 4. Test passed. Means we have symmetry about the polar axis. Okay, about this line right here. There's symmetry. And test 3. You replace the r with negative r. That looks just like test 1 in application, so the test fails. I don't know if we have symmetry about the origin or not. So there's your polar axis, there's your pole. Do we have symmetry about the pole or not? I don't know. Okay, but the interesting thing is we can graph this. This is extremely easy to graph. R is 4 is just a circle of radius 4. Look at that. That's full of symmetry, right? That has symmetry about the line pi equal over 2, y equals pi, or theta equals pi over 2. There's symmetry there. There's symmetry about the polar axis, which the test concluded we had. There's also symmetry about the pole, origin symmetry. But the test was inconclusive and didn't tell us that. So it certainly can be the case that you have the symmetries. Yet the test fails, and therefore you don't know from the test that you have those symmetries. Okay? The test is not perfect, in other words. Okay? If you pass the test, you know something. If you fail the test, you don't know anything. Okay? All right. So I'm going to stop with the examples right there. Okay? And the reason being is this is, well, a nice tool, and it's a fairly simple tool to apply. It's not terribly, terribly important for you. Okay? So what else are you going to be doing in this section? Well, you're going to be plotting points to create graphs. To that end, what I would like you to do is at the very end of the section, the author has a box he calls Media. And in that box there are links where you can look at graphing, polar equations, part 1, and graphing polar equations 2, part 2. And these are nice illustrated graphs. You can also watch animation of the polar equation, which is a nice thing to be able to do on a computer that we can't do on a board. And if you're interested, you can look at the last one on graphing polar equations on your calculator. Okay. All right. Now, finally, what I would like you to do is, if you look at just before this in the section, the author has what's called a summary of curves. And these are the variety of different curves that are created out of polar equations. The circle, what's called the cardioid, the one-loop limacon, the inner loop limacon, the lemon skate, the rose curve for both even and odd, and Archimedes' spiral. I don't expect you to know these, okay? That's not the point of asking you to look at these. The point is for you to look at these graphs and look at the equations and get a little bit of an appreciation of what kind of graphs polar equations are designed to create. Okay? Just like with rectangular equations, we can see that their strength is things like lines. What you can get an appreciation for here is that these curved shapes are more easily created out of polar equations. Okay? Just review to get an appreciation of the curves that polar equations generate. That's the point of this, okay? All right, so very short video today, thankfully. We are now up to the time to take our exam. So let me reassure you that this exam is not intended to be a high-stress event for you. I'm sure many of you, as just like many people in the world, already have a lot of stress going on right now. So let's take advantage of the opportunity we have to make this a very low-stress exam for you. Okay? I'm going to send out the exam to you on an email, and I want you to think of it as a take-home project as opposed to a formal exam. Meaning, I don't expect you to sit down with a timer in a closed room and work this exam. Think of it more as doing homework, okay? You write up the exam, you solve the problems, you take pictures of the problems, solutions, or PDFs, however you want to do it, and you email them back to me, okay? And that's it. Again, this is supposed to be a low-stress, relaxed environment for you, and please take advantage of it and do a good job on this. So when you write your exam, make sure you write each of the questions individually on a own sheet of paper so it's very neat and clean, and make sure I'll be able to read it when you send it to me, okay? All right, so I'll be getting that exam out to you tomorrow, and I wish you the best of luck. You should have about a week to do the exam, so that way if you have a lot of other things going on or hectic things at home right now, you should still be able to find some time to devote to it in the following week, okay? All right, so best of luck to you, and we'll get that exam to you soon.